Bene, buongiorno a tutti e benvenuti alla quinta edizione del Galileo Festival dell'Innovazione, manifestazione diretta da Massimo Sideri, Innovation Editor del Corriere della Sera, promossa dall'Università di Padova e da Venezia Post. Vi do subito appunto il benvenuto a tutti gli studenti dell'Università di Padova, ai tantissimi studenti che sono arrivati da tutta Italia per partecipare a questa 3 giorni dedicata all'innovazione che trasformerà Padova in una capitale nazionale e internazionale appunto dell'innovazione e del trasferimento tecnologico. Io do subito la parola per l'intervento di saluto al prorettore al trasferimento tecnologico e ai rapporti con le imprese, professor Fabrizio Dughiero, a cui tengo a dare il nostro ringraziamento per l'assistenza e il sostegno che ci ha dato in queste settimane. Prego.
Grazie Antonio, e per rispetto al nostro ospite parlo in inglese. On behalf of our rector, I would like to welcome you at this beautiful room. And the road to a new entrepreneurial renaissance is traveled by cities with creative communities. These communities actively participate in promoting international talent mobility, encouraging connections among the knowledge nomads who move around the world and the resources and talents rooted locally. With these few words of a friend of mine, Piero Formica, I would like to welcome you. Galileo Festival of Innovation is becoming a sort of a living room, or better, a Renaissance workshop where people can share own ideas by talking and expertise by doing. The 5th edition of Galileo Festival gives you the chance to attend more than 50 events, workshops, roundtable, with international outstanding speakers. Moreover, the Innovation Village outside the doors of our university show some of the many research laboratories and activities active in our departments. But today is a very special day. We have the honor to host in the room where Galileo Galilei taught 18 years, a long period, a Nobel Prize, André Geim, who is one of the father of graphene, the material of the future. I would like to thank him for accepting our kind invitation, and Massimo Sideri, who is the director of Galileo Festival. But I would like to thank all of you for your active and passionate participation to this event and to all the events of the next 3 days. Thank you very much. Enjoy.
Grazie al prorettore, al professor Dughiero, che veramente ha dato un contributo importantissimo all'organizzazione di questa quinta edizione del Galileo Festival. Un contributo importantissimo che tutta l'università che ci accoglie oggi e che apre le porte non solo alla città di Padova, ma a tutta la Regione Veneto e a tutta l'Italia. La quinta edizione del Galileo Festival che apriamo questa mattina è un laboratorio, l'abbiamo definito così. Sin dalla prima edizione ha sempre avuto questa connotazione di piattaforma di collaborazione e cooperazione. Tutti i dipartimenti dell'università partecipano alla costruzione di questo progetto, molti partner nazionali ed internazionali partecipano alla costruzione di questo progetto ed è questo che rende questa manifestazione assolutamente unica. Permettetemi di ringraziare quindi i partner che hanno sostenuto e supportato la realizzazione del Galileo Festival, cito quindi Dompè, cito Banca Generali, l'Istituto Italiano di Tecnologia, Padova Fiere, Vodafone Italia e ancora Bertos, Cortellazzo e Soatto e G-Planet. Vi dicevo, è una manifestazione internazionale e non a caso la Commissione Europea collabora a questa quinta edizione del Festival dell'Innovazione. Quindi io darei subito la parola a Fabrizio Spada, il direttore della rappresentanza di Milano della Commissione Europea, che è qui con noi oggi. Buongiorno.
Grazie, buongiorno a tutti, sono molto lieto oggi di essere qui con voi. La Commissione Europea ha deciso di collaborare con questa manifestazione perché In Europa l'innovazione è molto importante ed è nel lungo periodo l'unico motore della crescita economica. La Commissione europea ne è cosciente e finanzia programmi molto importanti per l'innovazione, fra cui Horizon 2020, che è un programma di 80 miliardi di euro nel periodo 2014-2020, proprio rivolto all'innovazione. È un programma molto importante che noi cerchiamo di promuovere anche in Italia, che è un paese che da sempre ha a volte delle difficoltà ad accedere ai finanziamenti comunitari, e siccome l'Italia, come sapete, è un paese in questo momento che è molto oberato dal debito pubblico, ci sono pochi fondi per l'innovazione, è molto importante che università, ricercatori, piccole e medie imprese italiane conoscano questo strumento e cerchino di sfruttarlo al meglio, perché è veramente importante per un paese che sia fatta ricerca e innovazione, perché senza di questa c'è il decadimento dell'industria e quindi dell'economia. Per cui siamo particolarmente lieti oggi di essere qui al Festival dell'Innovazione dedicato a Galileo, e siamo molto lieti di sentire tutti i ricercatori e tutti gli esperti in questo campo. Buona prosecuzione dei lavori. Grazie.
Grazie al direttore Fabrizio Spada. Non ci tratteniamo oltre ed entriamo subito nel vivo di questo Galileo Festival. Lo facciamo dando la parola lo definirei il Deus ex machina di questa manifestazione, Massimo Sideri, Innovation Editor del Corriere della Sera e Corriere Innovazione, che chiaramente dobbiamo ringraziare per un contributo fondamentale alla realizzazione del festival. Io lascio la parola al nostro direttore Massimo Sideri, a cui do il benvenuto. Ringrazio voi in sala, ringrazio chi ci sta seguendo in streaming per strada, chi ci sta seguendo via YouTube e via Facebook. Vi aspettiamo al Galileo Festival oggi pomeriggio, domani e sabato. Grazie ancora a tutti, grazie a Massimo Sideri e benvenuto.
Grazie Antonio, grazie a tutti quanti. Allora, siamo alla quinta edizione, la terza edizione che ho l'onore di dirigere. Chi ci ha seguito gli scorsi anni già mi conosce. Abbiamo fatto un grosso sforzo, ce lo dobbiamo riconoscere, con l'Università di Padova, il Comune, Venezia e Post, il Corriere della Sera ha dato il suo forte contributo, e chiaramente quest'anno abbiamo pensato a voi, e il nostro obiettivo era ogni anno alzare un po' l'asticella, quindi abbiamo pensato come possiamo fare per fare un passo avanti rispetto all'edizione comunque di grande successo dello scorso anno, e in quest'aula che è stata di Galileo Galilei abbiamo pensato a un premio Nobel. Quando abbiamo pensato a un premio Nobel, io ho iniziato a pensare ad Andre Geim, premio Nobel per la fisica, per i suoi lavori sul grafene, però vi dico la verità, non pensavo di riuscire a portarlo qui, invece ci siamo riusciti anche grazie all'Istituto Italiano di Tecnologia, e quindi lo presento perché siamo qui per lui. Andre Geim, Regius Professor and Royal Society Research Professor, University of Manchester, premio Nobel per la fisica nel 2010. Andre Geim, welcome. Thank you very much. Thank you.
Thank you, Massimo.
And
Thank you.
avremo uno speech del professore, di Sir Andre Geim, e poi vi prego, approfittiamo di questa occasione perché sapete non capitano spesso, fate delle domande, e fate anche, se volete, delle domande in italiano, ci pensiamo noi a tradurre. Comunque approfittiamo di questa occasione. Thank you very much, sir.
Thank you. Okay, now we switch into English. Sorry, don't speak Italian at all. Okay, but it's a pleasure to be here. So, can we, during the next 30 or so minutes, I'll give kind of an overview, trying to make it both informative and educational and not so boring to listen. After that, please prepare your questions. I'm quite happy to answer all of those. It's actually what I like most, rather than giving lectures, answering questions. So when someone gets an award, especially such a big award as Nobel Prize, usually two questions appear from the audience or otherwise. Okay, how? How did this guy get the Nobel Prize, and why? Why he did it? Why not me, for example, and so on. So I'll try to answer those questions, tell the story behind first, and then explain why actually not me, but why this material graphene attracted such a high accolade. It's all started about 25 years ago when I got my first university position, tenured position. It was in the Netherlands, and I was doing happily my normal research for which I get paid, for which I get money and so on, something very theoretical, no relevance to the real life at all. But people were interested, and I was doing fine. But I thought life is too short to do something all the time the same from your scientific cradle to your scientific coffin. I didn't want to do exactly the same. So I started doing what else can I do? To do something, you need to have facilities, and facilities were around, not so great, but one of those facilities shown on this slide was very large magnets we had there. They required a lot of electricity, kind of all University of consumes during the daytime, presumably to run just a single magnet. And they were not state-of-the-art at all. They were there for the last 30, 40 years. No one actually knew what to do with those magnets. So I first sort of kind of felt responsible to do something with this old age facility. And once upon a time I came with the idea, what happens with water if you put it inside very high magnetic field? Just water, nothing else. Magnetic fields are about 20 Tesla, which means they are kind of 10 times stronger than magnetic fields which you experience if you, for example, go to a hospital and have a magnetic resonance imaging scan. This sort of facilities in a relatively small volume. Why I was interested in water? Because somewhere at the back of my head there was a phenomenon called magnetic water. Allegedly, if you have just a tap and put a small magnet around this tap, people say that the scale disappears on your kettle or in your hot water tubes and so on. It's very controversial phenomena. There is no consensus about this phenomena, and I can't scientifically contribute at this moment in describing this phenomena. Hasn't done enough work, but the idea was that if a small magnetic fields do something with water, what would happen in the water when you put it in 10, 100 times stronger magnetic field? So that's once upon a time. I pour water inside the magnet. That's not what normally scientists do. They don't pour water on their expensive scientific equipment, but okay, I did this with a simple expectation that the water would end up on the floor. Not so easy. After a few minutes of, what the hell happening? After a few minutes of tinkering, I found out that the water started levitating. You're looking from the top, from here, inside what happening somewhere. This place, water is green because I shine laser light to make it easier to be visible. And this is the ball, like a tennis ball, which levitates inside. And it was spectacular, but I'm reasonably well educated to realize that it's not an anti-gravity machine. So the phenomena behind was not known to Galileo Galilei, but it was known for 100 years before. It's diamagnetism. So everyone, we, chairs, glass, everything inside us and outside us is a little bit magnetic. you don't notice this magnetism because it's really feeble, 1 billionth, 1 million. So essentially people always thought that magnetism is really such a small phenomena, this called repulsive or diamagnetism, that you wouldn't you would require really very strong magnetic fields to see and scientific equipment to measure this. This is what people assumed. They didn't thought that it's possible. Good Lord, what's happening? They usually thought that you can't really see common things to be compensated the gravity, but you put few numbers into equation and find out that the fields which I had were enough and gradients were there enough to levitate water. What that was kind of not surprising for me. Surprising really was that my colleagues next morning didn't believe that. They say you pull our hair. And my colleagues worked for, I don't know, some of them for 50 years professionally with. Okay. Yeah. Thank you. So, is it better now? Okay. So my colleagues didn't believe me at all. Professional people working for 50 years with the same kind of facilities, and there were quite a few facilities around the world. So the next few weeks I have to spend to persuade everyone that this phenomena is as strong as I said, as they didn't believe, and my colleagues came with all brilliant ideas what else you can put inside, for not only water, you can put beer, you can put red wine, you can put all those vegetables, name it, everything essentially levitates approximately at the same position, approximately in the same magnetic field and so on. So I got fed up at certain point of showing demonstrations to the colleagues and so on. So what else, okay, because no one believed it, there was a point, okay, to show something which really people would remember. And this was a small frog which I put inside and make a picture of this, and this frog make all kind of headlines, and I'm sure this frog was also featured in Corriere della Sera, okay. So I even have make a small movie. Was very hard experiments to make. I'm a physicist and I usually deal with dead objects, and this object was not dead but jumping and sticking, and it was very hard experiment to do. But eventually the outcome of this, it's in many textbooks these days, and sometimes at the conferences people come to me and say, oh, you know, I have no idea what graphene is, but your frog. Yeah, that's kind of pleasing, and for those people who think that science has to be boring to be interesting, it shows that it's not the case. And to rest my case, I'll show you a letter I received that kind of 20 years ago, which reads, okay, I'm 9 years old and I'm very interested in your frog and I want to become a scientist, okay? So very pleasing letter. So that's kind of a story which starts, after which you start thinking what else you can do, make your life not as academic, not as boring as it usually is for us, okay? So the next this kind of random experiment what's something wrong with this slide? comes with this magnificent animal called gecko, and you know that they can easily climb walls and stick to glass ceilings. What you probably don't know, the mechanism behind this sticking ability of geckos. Essentially, people, well before myself, found out that the mechanism is quite simple. Toes of geckos are covered with tiny, tiny hairs, like my hair, but okay, much, probably 100 times thinner, and there are billions of hairs covering toes of those geckos. When you take your hair and try to touch any surface, there would be a force between your hair and this surface. You wouldn't notice this force because it's so minute, it's 1 nanonewton, 10 nanonewton, 1 billionth of a newton. But geckos have billions of those geckos on their toes, and when they are all together contributing to the force, it's enough. It's about Newton. It's enough to keep them on those ceilings. Okay, it was so simple idea that the nature offered, and the size was the same I was doing in my lab, in my other incarnation research, that I thought, why wouldn't we try this? And we did try, okay, half successfully, okay. This is the forest of artificial hairs I have done in a plastic. Unfortunately, the hairs clumped together, so the tape didn't work many times, no many attachments like geckos can do, but it still worked. The original idea was to make a gecko glove, give it to some of the worst students I have, and put him outside a window and see whether he would be able to climb or not. Unfortunately, it was only very expensive to make. It was only 1 square centimeter I managed to do, so I have to finish with a toy instead of a student. But at the end, this paper led to a new direction. Dry adhesives, and a couple of years ago I saw a demonstration of a big guy, bigger than me, hanging from a ceiling, okay, using a gecko glove. But again, the problem that you can't move with those gecko gloves. You can only attach one, probably a couple of times, and this is it. But we'll see whether this direction goes. Having dealt with geckos for a while after the frogs, I have done many other experiments, and but some of them were successful, some of them were not so successful. But what unites all those experiments were that they were random. I didn't deal with geckos, I didn't deal with frogs, I didn't deal with water before. It was out of my ordinary path of work. So the next comes is the subject which I received the Nobel Prize. It's also by the same kind of untrodden path. Okay, I thought it would be a good idea to have very thin graphite films and study their properties. I have never in my life before dealt either with carbon, nor with graphite, nor with anything else, but okay, somewhere at the back of my mind there was an idea that if you take a chunk of graphite and try to polish it to very thin layers, you might be able to find something interesting. So at the end, after many tries, we found out that the best way actually to make thin graphite, not by polishing, not by using any very scientific equipment, but just the usual sticky tape, scotch tape, and so on. So what people did similar to me before, they It's a very common experiment, okay? I'm pretty sure many people at the University of Padova and probably some people in the audience know what is atomic force microscope or use other scientific equipment to study surface of graphite. It usually works like that. You have a graphite bit, you take a Scotch tape, attach to this, pull out your Scotch tape, make your surface clean because graphite peels very easily, and then study this clean surface of graphite and throw away this Scotch tape because it's junk on the surface left. So what people didn't realize is that with throwing this piece of Scotch tape, they perhaps had thrown their Nobel Prizes as well. Instead of using a clean surface of graphite to study something, we looked more carefully at the surface of what is left on the tape. And when you know it, it seems all very so easy. You take this Scotch tape, like it's shown here, put it under microscope, shine the light through, and then you see something on the tape under magnification. This is dark region, this is graphite. Thick graphite, it's dark, it's non-transparent, it behaves like a metal. This is what in your pencil trace, which makes the pencil trace dark. But then you see some pieces which are nearly transparent. And then it was kind of a eureka moment because, okay, transparent metal, it must be really thin. And this is where we started by seeing those small transparent pieces on the Scotch tape, and then it took us many, many months to do what we have done later, to study those pieces of graphene. So, but why I said that it was a eureka moment? Why I was excited to see those junk pieces on the Scotch tape? Again, education helps, education, and education, as people say, because if you look around what surrounds us, we live in three-dimensional world, and there is always width, length, and height, 3 dimensions, and materials or any objects we are familiar with, they all have these 3 dimensions. You won't find objects with one of those dimensions missing. The same refers to the materials. It can be very thin material, but it still has height. The material which is we saw on the tape is essentially had no height because it was as thin as possible. Why it is so? Why all materials are all 3-dimensional? Because there are some powerful theorems which essentially say that it's impossible. You can tell differently. You can say, okay, nature is smart, okay, because there are 3 dimensions available. Why do I need to use all 3 dimensions or 2 dimensions? I'll try to use all 3. And this is how crystals or everything else, including us, grows in all 3 dimensions. And in 2 dimensions, it's not only hard to find, it's more important that it's fundamentally forbidden. So the trick essentially was the same. The nature creates 3-dimensional materials. You can't actually overrule this. This is the only way to make materials in nature. But you know that materials, take for example, any material you know, it's a crystal to a certain extent. All those materials, well, many of those are in crystal form, and it consists of atomic rows and atomic planes. And then you can ask yourself a question: what if I have very tiny tweezers and pull out one of atomic planes, individual atomic planes? This nature allows this because you grow at high temperature, but then can do this pulling out individual plane at a temperature much lower than the temperature at which you created the original three-dimensional crystal. So that's what we have done. It's not forbidden in nature. You can do this. And this is how graphene looks like. You see a millimeter-sized crystal on a surface of something, and it's visible by your naked eye. And it's a monocrystal, perfect rows and perfect plane of atoms. We know this. We can put this crystal in transmission electron microscope and indeed see all those atoms and holes between those. So it's essentially like this, what we see there. Fine, okay. We have proven that there is this kind of materials which are one atom thick, the thinnest possible in nature. It's not completely one dimension absent, but in terms of material science, it's kind of, there is no point, you can't go any thinner than this one because it's one atom thick. The next question is, so what? Okay, yeah, simple material, simple structure, and so on. And if it would be the end of the story, it would be not so interesting. It would be, okay, a small niche in a very huge subject of physics and material science. But we had a careful look at the properties of this material. It's of course the thinnest possible material, but it's turned out to be the strongest material. Of course, you have to take into account that it's only one atom thick in cross-section, but it's the strongest material. It's the stiffest material we know. At the same time, it's stretchable. It can be stretched realistically by up to 20%, and it's as pliable as zinc. It shows record thermal conductivity. It shows amazing electronic properties. I was involved in studying the second part of mostly the second part of this table of superlatives. So it's better, it's stronger, high-end, etc., than many other materials. But probably the most interesting part, its electronic properties. This is what originally attracted attention of ourselves and many other people, and only later it went in all other directions. So I'd like to give you a very short crash course about, okay, what kind of new science is inside. And the new science comes from the fact that essentially when we're trying to describe a world around us, we describe it in terms of, Newton equation, Galileo equations, and or which is nowadays known as Schrödinger equation, for objects which are moving with a speed much lower than the speed of light. This is one part of physics. Another part of physics deals with Einstein kind of physics, where you move objects with the speed close to the speed of light. This is a domain of particle physicists, cosmologists, and so on. And material scientists usually deal with the first part of this world, and particle physics is completely different domain. So graphene make a bridge between this kind of particle physics experiment and classical physics experiment. And so what it has done, we can do something on a tabletop what CERN or particle accelerators cannot do, and whatever most powerful telescope can't probe looking into another galaxy. So I'll give you a couple of examples to give you an idea what kind of physics did come out of studying electronic properties of graphene. If you drive by your car into a wall, you know what would happen, okay? I don't need to explain. But if you would live in a quantum world, in a world where electrons live, there is something strange. Many of you probably, at least those with university degrees, probably know that there is a phenomenon which is called quantum tunneling. In this case, the scenario is slightly better. If the world is not very high or very wide, you still get your quantum car burned, but a ghost of this car can go through the wall, a part of this car. Quantum nature of small particles. But if you live in a quantum world and move at the speeds close to the speed of light, then something really strange, even stranger than in the middle picture, occurs. Imagine that your car and you live in a world which follows the same rules as electrons in graphene moving through graphene behave, then you try to create a barrier. However high or however wide you make this barrier, your car would go through any of those barriers without leaving anything behind. It's called Klein tunneling. This phenomena was known for 70 years, but presumed not to be tested experimentally. In graphene, this phenomena could be not only tested, but actually this is one of the reasons why graphene is having the highest conductivity of all other materials. You can't really confine electrons from moving through all kind of obstacles. So it's a routine phenomena in case of graphene. Another example, also very kind of fundamental example, is the following. Okay, you know the periodic table, okay, yeah. Can you press a button? A periodic table, and there is something like 115 elements in this periodic table. And if you are a fan of science fiction literature, you know, sometimes some extraterrestrials come in and so on with some very heavy metal-built rockets and other equipment. So it's fair to ask a question, okay, if you create a very heavy nuclei, say 200 protons inside, would you still be able to extend the periodic table? This question has been asked before, and initially someone has to do something. And initial answer is that seems to be fine. It's just the same Bohr kind of a model. You have nuclei, you have electrons moving around this one. So you put more and more electrons and everything seems to be fine. So for science fiction writers, it looks all right. But then if you take into account that those electrons move at a finite speed, not at a low speed, then it turns out that if you have something more than, say, to 170, the charge of your nuclei, electrons can no longer be on stationary orbits. They collapse. They go on the center of this attractive force, on the center of this nuclei. So the answer is that no, in our universe at least, you can't build your periodic table above, say, 170, even if you find some stable nuclei. So where graphene comes into play? Graphene, because it mimics what happens in a real universe, you can make up this experiment relatively easy. but not so harder to show you. So this experiment has been done, and indeed, if you go create a couple of charge center there, then you see a collapse of electrons on your neutral center. So that has been verified thanks to graphene. So I hope that with those two examples, and despite my equipment is not working, scientific equipment worked fine during experiments, at least in the lab, this brings you a lot of quite unusual phenomena and so on. But people in the audience, especially with kind of a skeptical mind, okay, would probably say, all right, those examples, and there are many similar examples of nice physics. What do they really matter? What about real stuff? What are the applications when I can get something in my mobile phone in my house or something like that using graphene? Okay, of course. Okay, when you have something with so many superlatives, you immediately start thinking how I can use this material around, whether it can give me something new and something competitive. And a few years ago, it was completely impossible to even speculate about this. But about 3-5 years ago, people motivated by how nice properties of graphene start thinking about production. Now graphene can be done in tons. It can be done in square kilometers if it's required. And after the production of graphene, not by this Scotch technique method, which we still use in our lab, but when it can be done industrially, people start thinking and start moving into applications. There are many of those applications. Okay, some of them are very far in future. Some of them are I don't know whether they're realistic at all or not, but okay, more realistic. The longer we live, the more realistic they become. Okay, for example, people use different composite materials to improve plastics. There are graphene cars. Where some parts of the cars are made with graphene-enhanced plastics. There are graphene batteries, where graphene is put inside to improve their life for a few percent. It's still first very early applications of graphene, but it's coming. We'll have to live another 10 years to see really those products entering in our life. But there are hundreds of companies around the world who are actively working in this direction, and some of them already making consumer products. So is this it? Actually, not quite. This is graphene scientifically has been done and dusted, but it turned it turned out that graphene is not alone. Graphene has a lot of other materials, its brothers and sisters, cousins, and so on, and all is in common, that they are all one atom or one molecule. This is already has been known for 10 years, but people focus mostly on graphene itself. But now there is a lot of efforts during the last 5 years to study other kind of materials. Okay, they are not in industry yet, but we have now a library of probably a few hundred of those materials which are actively studied. So in addition of graphene, you can do a lot of experiments with other materials. This is a table of those. I don't want to go through this table, but it expands the opportunities. If graphene fails for a certain application, you can look at this table and see what other material do you need. Okay, magnetic material, it's there. You want to have, instead of conductive, you want to get an insulated material, it's there. You want a semiconducting material, it's also there. So there is a lot of opportunities there. Moreover, you can do something beyond even that. Okay, the universe after graphene expanded. We were 15 years ago, we didn't expected that those materials could exist, and now we have hundreds of those. What we can do with those materials, you can study not only a single layer, you can study bi-layer, tri-layer, whatever number of layers you want. They're still very, very thin materials, and then you can do something like that. That's what we're doing now in the lab. Stacking those materials in a sequence we think is good to create new kind of materials which nature can't create. It's kind of a Lego game, but now instead of those bricks in Lego game, we have atomic planes which we can use and make up something nice, something interesting. So this is not only cartoon which are shown, but this is the real pictures you can see. In this case, okay, it's a simple stack. We can do much higher. In this case, we apply voltage between two graphene sheets, inject electron and holes into another one molecule thick material called molybdenum disulfide, and light comes out. Oh dear me! And light comes out, yeah, it's works like LED, but this is a flexible, very thin, flexible LED. One can imagine that you can your wrist with a band on your wristband with kind of with LED. Working on this, don't need to make LED hard, flexible, and so on. We'll have to see whether this direction will leave us. Yeah, okay. But this is very intensively studied direction. So my message to those essentially who are dealing with graphene in this audience, and I believe there might be a few people here, that graphene is not the only material. It has become a shorthand for many other materials. Okay, I'm no longer doing much graphene. I'm equally using other one atom or one molecule thick materials. It's a really huge area which is not going to die for the next 50 years. It's probably would be forever. It becomes a kind of a toolbox. Within our toolbox, we have copper, we have gold, we have iron, and now we have all this variety of materials which are called graphene for brevity, and we can use this one. So my final slide, because my time is up, essentially is directed for young people in this audience, okay, especially for young people in this audience. You have a pencil and you draw a line on a piece of paper. So what you see a pencil trace, okay? It's dark because pieces of graphite shred by the pencil lead are left on the surface. If you take a magnifying glass and look carefully through this trace, you'll find out that some of those pieces of graphite are not really as thick as others. Some of them are very, very thin, as I shown you on a transmission optical microscope photograph. They are transparent. If you spend a couple of hours, as I did about 10 years ago, and looked in a microscope through the pencil trait, even in a single pencil trait, you can find graphene, the material which got the Nobel Prize. So the message is that this material was in front of our eyes, literally under our noses for the last 500 years, but it took only to the 21st century, to this millennium, to figure out that material is in these pencil trays, and this material brings so wonderful properties. So this probably tells us that we still know very little about the world around us. Thank you very much.
Please. Thank you very much, Professor. And I'm sorry for a technical problem, but you know this was the room of Galileo Galilei, and we have an old technology to respect the spirit of Galileo Galilei. I'm sorry. So I call now I call Marco Polini, responsible for theory and technology of 2D materials of Istituto Italiano di Tecnologia di Genova. Welcome. And Marco and Vittorio Pellegrini. Perhaps some of you remember the lesson last years of Vittorio Pellegrini about the graphene. So Marco Polini and Vittorio Pellegrini were my first contact with Andre Geim. So thank you very much, Marco, for this. Now we have a Q&A session. So if you have some question, we can try to have a talk with Geim. Perhaps my little son Riccardo have a question. We have a microphone for Marco Polini. Sorry. So, Professor, we understand that graphene is very important and very interesting for science. But I have the first question: why graphene is so popular? This is amazing, because we don't remember a lot of Nobel Prize winner, but we know you and graphene. Why?
I think I spent the last 40 minutes trying to persuade you. Should I repeat the talk? Because it's not one material, it's many materials, okay, which are now referred to as graphene-like materials. So any scientist can probably think about something from his or her perspective. How can I use this kind of materials in my own research? And they voted with their feet to move into this direction, and most of them were not disappointed by switching the area of research. The same refers to industry, because people in industry sometimes look out what you can do with how I can improve my production and make additional competitive advantage to my products if I use this material to do this and that. Okay, this kind of was as a magnet for this area for the last 10 years for scientists, but particularly during the last 5 years, it also has become attractive for entrepreneurs, because they see a lot of possibilities in this product.
I broke the ice. The second. No, just a moment.
Thank you. Thank you very much. I ask you kindly if you can say some words about the collaboration, the relationships of you with Konstantin Novoselov, and the help he gave you in this important discovery.
Well, that's a tough question to answer, because usually when you have a Nobel Prize collaboration between supervisors and students, they fell out after the next morning a prize has been announced. Kostya was my PhD student at this time when we studied, and he was most active in this research. He worked 24/7 for many years. He surely deserved by his work a part of this Nobel Prize, and I'm very happy to share. But I said many times, unfortunately, I would like to see many other people to share this Nobel Prize, because these days I'm always irritated when people say Nobel Prize, graphene discovered by Geim and Novoselov. There was a collective, a group of 5-7 people who worked there. There were many international colleagues who were maybe just a few steps behind. So this is the only thing, but it's not my job to pick up winners. The Nobel Committee picked it up, and I'm very happy that at least I'm not alone in this prize. But I would like to see other people to share this as well. Thank you.
Grazie. Posso parlare in italiano? Grazie. Primo Levi, 40 anni fa, scrisse un bel libro, L'atomo di carbonio nel sistema periodico. Era l'inizio del grafene. Oggi il grafene mi sembra un gruppo, una famiglia di atomi che stanno insieme. Mi chiedo, queste famiglie diverse che lei ha rappresentato, le formule, vivono in pace o in guerra? Si vogliono bene o si odiano? Cioè, qual è l'importanza per l'uomo, per la vita dell'uomo, questa scoperta? Grazie.
So he's saying that, so there was an Italian, very famous Italian writer, Primo Levi, that wrote a book, actually, was not aware of that, and he wrote a book, The Atom, the Carbon Atom, actually. But, so the question is, so he sees as graphene and all those materials that you talked about as a, families, and so do they live together well? Are they in war and peace? And what's their role for the human being, actually? So that's the question, I think. Yeah.
I didn't quite understand who live together happily.
Well, is this family of atoms that live together in war and peace that make the materials, actually? So moly, sulfur, tungsten, carbon. Do they live well in a peace or war, and what's their use for the human being? I think that's the most important thing that he was asking. Yeah.
Well, it's a very philosophical question, I guess, but atoms as humans, they live in peace if they feel so, or they make war if they feel at war. So it's in experimentally speaking, you can put those atoms together in an arranged manner, say molybdenum disulfide monolayers and monolayers of graphene, and they improve. For mutual benefit, they improve their properties. Something which comes on combination is not something which comes from any of those individual materials. So it's a good strength, but without without a detailed knowledge about the nature, without taking into account a different nature of the product, you might find something completely different, completely counterproductive, okay, something which doesn't work if you do not take into account the existing properties. And having said it, immediately reminds me of the European Union when some of materials and some nations live when you understand culture, they live happily next to each other, but when you try to force them in some awkward positions, then there is a breakdown in the relations, as we have seen experimentally with two-dimensional materials and seen experimentally with the European Union during the last 10 years.
Posso, magari aggiungo una cosa, io sono un fisico teorico, quindi una visione un po' particolare, però cioè, contributo per l'uomo non me lo immagino solo in termini di necessariamente magari di un'applicazione come è stato discusso, insomma, ma mi faccio dire che è un materiale che ha aperto, dal punto di vista di fisica teorica, come ci ha brevemente detto lui, ha aperto veramente un pianeta, le diceva appunto che gli elettroni per esempio in questi materiali si comportano in maniera veramente strana e tante idee e su cui si sta lavorando ora, si lavorerà per 20 anni, sono nate a partire dal 2004, 2005, 2006 quando il materiale è stato scoperto, insomma, quindi dal punto di vista del contributo per l'uomo mentalmente è stata assolutamente una scoperta notevole, insomma.
Un'altra domanda? Lì, in prima fila, qui.
Thank you. Okay, first of all, thank you very much for your comprehensive and at the same time very enjoyable presentation. I believe that that is fundamental when we can transmit science in this way. It's probably for the young people that is really important. Coming back to the question, I would like to get back to the point you mentioned about people and companies approaching you asking about application. From the scientific point of view, I've seen the evolution of carbon nanotubes sort of grow and then stabilization, let's say, of the activity, and even because it was more or less simultaneously with the growth of graphene, the rise and the growth. What I've seen is that there is most of the time some missing culture in the way of maximize the benefit coming from the application of the new materials. How important do you believe is the capability for scientists in general, for university, of research center, to transfer knowledge to potential applicators of the technology we are developing to get the most we can from those materials? Because you list a lot of applications, but in most of the cases I've seen people not using properly the material for the possibility they have. Thank you.
Yeah, it's a good question. It's about, okay, how to transfer our knowledge from academia to industry and whether we are doing this successfully. Okay, first of all, I have to point out that typically for any material it takes 30-40 years before you really start seeing commercial products out of this. For graphene, there are already commercial products on the market, and it's probably yet another superlative of this material that it's managed to move from academic floor to consumer products very quickly. Of course, you mentioned carbon nanotubes, and this helped because much of elementary knowledge about graphene came from, it's not just popped up, it came of the basis of, as Newton said, we were standing on shoulders of giants, okay, so it's helped to know the previous properties of carbon nanotubes. So what distinguishes from probably carbon nanotubes, that graphene is a very versatile material and there are so many different sisters and brothers. as concerns in industrial applications, it's, you know, realistically speaking, production has been developed 3, maybe 5 years ago. So this is when industry started trying. At the moment, it's not revolutionary programs. At the moment, it's diffusion. It's, as I said, slightly to improve the lifetime of your batteries, make your carbon fibers, if you cover them with an extra layer of containing graphene, they shatter less, they become more impact resistant. Then it's putting graphene into like thermal dissipator paste. It's improve energy efficiency of LED by 8%, not a revolution, but a significant margin. The graphene LEDs serve twice longer. You put graphene in tires, and tires shred rubber less because graphene increases thermal conductivity, and so on. There are, realistically, it's no longer wishful thinking. It's realistically those many, I probably can just at the back of my head name you about 10 different applications where graphene is already there. But we don't know, we usually, unless it's a marketing trick, we normally don't call those products graphene products because it's just an improvement of existing properties. Whether it will come, and I believe it will come to some kind of revolutionary applications where graphene brings something, not a marginal improvement by something else. That remains to be seen. It's not yet on the market, but we do need to spread the knowledge about graphene too, because you can't build the bridge from academia to industry from one side. Something has to come from industry as well to build a common bridge. It's tough, it takes time, but okay, people are working on this. I'm optimistic. Thank you.
Parlo in italiano, va bene, ok. Volevo chiedere al professore se, secondo la sua opinione, dopo aver prodotto dei materiali 2D, potremmo produrre anche dei materiali in una sola dimensione e se ci sono delle ricerche in questo campo.
So, since you've made 2D materials, can 1D materials be made, and is there any research ongoing on 1D materials?
Well, that's a good question, and we did ask this question ourselves. The problem is we live at very high temperatures. So we live at room temperature, and this is not 0 centigrades and not 20 centigrades. This is 300 Kelvin. So if, in principle, if you extract an individual atomic plane, then it's obviously possible, or at least feasible, to extract individual atomic row. But it would be much more susceptible to temperature. So thermal fluctuations, vibration would be much more important for 1D materials. And it's tough to make, and there are a couple of examples of those one-dimensional wires containing a single row of atoms. They can be made from carbon. Carbon rows are known, not investigated because they live for a few seconds, and also rows of, say, gold atoms are also could be seen and a bit investigated. So we are not at this stage, at least in terms of facilities we have in the labs around the world to study these systems, but eventually I think it's a possibility to come true.
you said that nature ate lower dimensions. So in this case, what make the graphene plane stable, so to say, against fluctuation, which typically destroys two-dimensional material, crystals better?
So the question is what stabilizes
Yes.
against fluctuations?
Even if it is two-dimensional.
If there are two factors which important for stability. You can't do the same trick with Scotch tape for many other materials. Say take gold, or you can't extract a single plane. So one important thing is that gross temperature should be much higher than room temperature. We work at room temperature. If we could do the same at liquid helium temperature, there would be many more other materials, but at the moment we are really limited to our ambient temperature. So this is one condition. A material should be really grown at very high temperature, bulk material, to allow a single plane extraction. The second important point is that those materials which allow individual atomic planes should be also very robust in terms of chemistry, because again, environment contains air, moisture, and so on, and in principle these days many people, including us, use so-called glove boxes, work in inert atmosphere to prevent individual planes being destroyed by moisture or oxygen. But even in the best glove box, there is still some remnants of oxygen and other chemical compounds that is destroyed. Graphene is not surprisingly the first material which was extracted, because melting temperature of graphite is above 3000 centigrades. At the same time, graphite is most inert chemically and thermally than any other material. So that's two conditions which limit the number of this kind of two-dimensional materials which are possible, but there are still a couple of hundreds those already isolated. Yeah, but this is a balance.
In the last slide you were presenting, you said that a pencil is basically a strike of graphene. And I was wondering, does it have all the same properties as graphene? Or, for instance, could we be able to draw a circuit, functioning circuit, and conduct on a piece of paper?
Okay. In principle, yes. There are pieces of graphene, and graphene is by definition only one material. Unfortunately, those pieces of graphene would be extremely small, so less than micron in size, so you can't really make a circuit. So it would be a very poor quality graphene, but it would be there. So, but our graphene, which is extracted by Scotch tape, which in academic labs it's still the preferred technique these days. It's 100 by 100 microns. It's much easier to make a circuit. But speaking about something simple, for example, mass production, I describe in tons production, is not very much different from what I described on the last slide. You take from a mine, you get graphite, chunks of graphite, put them essentially into a fruit blender, literally a fruit blender, and shake it for a few hours. You might add a little bit of ultrasound transducers, and at the end you'll get a kind of sludge or liquid which contains many of those one or few layers of graphene, essentially the same in the pencil trace, and this is the stuff which is used now for nearly all those products which I described, batteries and etc. etc. So it's a little bit different from people drawing pencil and so on, but it's a fruit blender essentially, which turns out to be most effective in terms of industrial production.
Buongiorno, parlo in italiano. Volevo sapere se nella struttura dello strato di grafene è possibile trovare delle impurità e se è una cosa negativa o può avere delle applicazioni. Grazie.
So can you find impurities on graphene, and if so, they bring in only bad things or they can bring also positive things?
Again, it depends, okay? If obviously trying to study properties of graphene, you try to avoid any impurities on this one, and fortunately it's possible to make graphene without any single impurity over the size of device, which can be 10 microns, a cross section of your hair. Not a single impurity could be found. So this is high quality devices usually studied in academic labs, and if you try to speak about future electronic circuits, this is what you like to get. But on the other hand, people intentionally can produce defects, vacancies, can put substitutional atoms to modify properties of graphene to the extent they would like to have. So it depends on what particular application you're aiming at, but whether you have impurity or not, what kind of impurities you have, it's again possibilities to tune your system to something you would like. It's a knob you like to use, trying to fit to a particular application in mind.
Se ovviamente sei interessato a quello che fanno gli elettroni, le impurezze danno noi ovviamente, no? Se vuoi guardare solo a quello che fanno gli elettroni, insomma, quindi per molte cose che si fanno in teoria e calcoli soprattutto è meglio evitarle.
Una domanda di nuovo qui.
Mi scuso se faccio una seconda domanda. Nel mio laboratorio di chimica, con i ragazzi di 14-15 anni, ho l'atomo di carbonio in 3 dimensioni, che è il grafene, con pentagoni ed esagoni. E assomiglia al pallone da football, è uguale identico. Per cui questo è il grafene senza impurezze. Le partite di calcio sono servite per evitare di fare la guerra. Poi a volte la guerra avviene nel campo di calcio. Comunque la Juventus ha vinto contro la Monaco. Mi auguro che vadano avanti le partite di football. No, a parte la battuta, mi scuso. Però sono contento delle nuove invenzioni. Però Fermi si chiedeva, quando ha scoperto la bomba atomica, se sarebbe stato uno strumento di pace o di guerra. Ecco.
Well, he's going back to the issue of war and peace. I don't know why he's obsessed about that, but he's so he says that. So I think he's a high school teacher. He has a chemistry lab, and I think he works with buckyballs because he was talking about soccer balls. But the question is again. I mean, Fermi, I think he was worried, when he was doing nuclear research about what was going to happen later, and is it going to bring war and peace? So he's asking again a similar question: is graphene going to bring war and peace? I think. E questa è la domanda, cioè se questo materiale è ossessionato da questa cosa qui, se questo materiale porterà giusto? Okay. Okay, so I think that's the question. Okay.
I haven't heard about many military applications of graphene. People try to use graphene for stealth fighters because it's absorbs light quite well, okay, but it's a stealth are there anyway. Another application I know is in nuclear industry, in civil nuclear industry, where graphene might help to solve problems like contamination by tritium and so on. So in all those areas, when you say word war comes to mind, okay, it's tritium decontamination now very popular problem in nuclear industry, and graphene is becoming very popular as a possible solution for this one. So I vote for 95% peace, 5% war.
So thank you very much. I think that we finished the time. Okay, the last question. Okay.
Molto veloce. Prima si diceva che il grafene sarà il prossimo, sostituirà il silicio. La mia domanda è, per quanto riguarda il riciclo, una volta prodotto, il recupero dai prodotti industriali, è più o meno efficiente, dato che il recupero del silicio è una delle nostre piaghe attualmente?
So he's saying in a prospective future where carbon and graphene will replace silicon, will be recycling more efficient than in silicon? Because it says that silicon, it's, you gotta recycle it now, and will it be easier to recycle when industry will make products out of graphene?
I'm not sure that graphene will make silicon obsolete. There is no point, because those materials can live happily in peace with each other, referring to the next question. So in a sense, okay, but what you're asking about an environmental impact of graphene. Okay, first of all, I have to say graphene is essentially graphite as a component, one atomic plates of graphite, and it was around us with humans as long as graphite was, for 500 years ago. And if you use a pencil, you probably know that you can chew this pencil, and the only danger of the pencil is probably if it's sharp and you sit upon it. Otherwise, it's completely harmless product. So people look very carefully already for possible negative health effects of graphene, and fortunately they didn't find any. There is even research, there is I don't know, it's very hard to translate into Italian probably for the horse. There is so-called gripe water. This is kind of mild painkiller which is given to kids before modern painkillers were given. It was given for hundreds of years to children to drink gripe water if they have something, headache or stomach ache and so on. And people looked inside, and there is plenty of graphene floating around in this one. So people speculated that we might have become immune to graphene already for so many years. So fortunately, no health hazards seem to be there.
So thank you very much. Finally we can say you are the father of a new kind of physics. Thank you very much for this lesson, and we hope to see you next year in Padua, perhaps. Thank you.
Thank you.